Hello and welcome back. We talked about divergent boundaries where plates move away from each other. We talked about convergent boundaries where plates crash into one another. Now we'll talk about transform boundaries where they kind of move side by side, usually in one direction relative to the other. Additionally, we'll also talk about a couple of additional topics. This is a little bit shorter video, so I threw a couple of other pieces of information to help round out how and what happens on and in the crust. But before we get going, let me give you the next part of the super secret code. It is the number 1. You got me? The number 1. One more time. It's the number 1. Okay, so again, back to our map of plates and as well as boundaries. On this map, transform boundaries are marked by the purple portions. You can see there are some longer portions of transform boundaries, but a lot of them are these small little bits that kind of connect divergent boundary areas. One interesting transform boundary runs along through California. The San Andreas Fault sits near this boundary. More on that here in just a little bit, but that's a nice long transform boundary where the Pacific plate is grinding next to the American plate going in different directions. All right, so in any case, transform boundaries. Again, this is where the plates slide kind of laterally past each other, roughly parallel to the direction of plate movement. They move and grind in about the same direction. The movement results in a lot of broken and shattered rocks, as well as numerous earthquakes. And these can be very powerful earthquakes as well. Again, the San Andreas Fault, which sits kind of right along a transform boundary. If you know anything about California and the San Andreas Fault, or if you've seen that movie with Dwayne "The Rock" Johnson, they can create a lot of earthquakes. The majority of transform boundaries are made by a series of transform or strike slip or faults, I should say, and they often connect two oceanic ridge segments and marked by fracture zones. So again, looking at the mid-Atlantic ridge, the divergent spreading areas are kind of staggered, and what connects them one to the next are these transform faults, and the series of faults make up kind of typically a boundary, sort of. There are yet other kinds of transform plate boundaries that connect to oceanic trenches or connect a ridge to a trench, but in any case, there's always this side-by-side movement. Transform boundaries can also extend into and onto continents. Again, just think of the transform boundary that kind of cuts through California. So a great example is the San Andreas Fault. So along the transform boundary between this portion of the Pacific plate and the North American plate, there's a series of faults. There's a bunch of faults. The San Andreas Fault is just one of them. Again, usually these transform boundaries are a series of smaller faults, kind of all squished together. So you get a lot of deformation and also a lot of earthquakes along the San Andreas Fault. Again, this separates the Pacific plate from the North American plate. So it connects ridges. Let me move me a little bit. It connects some spreading centers here in the Gulf of California, and it connects it all the way to spreading centers, divergent boundaries, all the way up to the small but mighty Juan de Fuca plate and ridges. Many of the earthquakes in California are a result of movement along this fault and boundary. One interesting thing to note, let me move me again, sorry. So the Pacific plate, again, is moving kind of up and to the left. This little arrow indicates the direction the Pacific plate is moving up and to the left, so it's that northwest. The North American plate, relative to the Pacific plate, is moving down to the right, so to the southeast. Los Angeles is on the Pacific plate. San Francisco is actually on the North American plate. So Los Angeles is actually heading north. San Francisco on the North American plate is actually heading south. Millions of years into the future, those two cities are actually going to be right next to each other. Now, humans will be gone by that point for a long time. But where those cities were will geographically be next to each other if current movement continues. Excuse me. I think that's all I want to say about transform boundaries. Let's talk about hotspots and mantle plumes. Not much to transform boundaries. So hotspots are locations where stationary kind of blobs of magma originating down in the mantle, called mantle plumes, slowly rise to the surface. They just kind of randomly happen. A lot of these mantle plumes and hotspots occur kind of in the center of large plates, and the idea there is because plates are so large, they're putting so much pressure on the center, the mantle under the center of these plates. Increased pressure is changing the chemistry dynamics of the mantle material, allowing it to melt. When it melts and becomes liquid, liquid is less dense than solid, so that liquid magma begins to rise, forming this mantle plume, creating this hot spot. Now these mantle plumes remain stationary. However, the plates over them will move. So the mantle plume, the hot spot, stays there, but the plate over it kind of moves around. And when this happens, you can see the actual occurrence of this, especially if these hot spots are generating and creating volcanoes. For example, the Emperor Seamount and the Hawaiian Island chain. Let's look at a diagram. Okay, let's look at the next slide first, and we'll come back to this. So here are the current Hawaiian Islands. The largest of the Hawaiian Islands now sits under the hot spot that's underneath. So this is the Pacific Plate. All right, it's very large. In the middle of that plate, the idea is it's so much pressure in the middle of that plate that it's creating a mantle plume below it that's kind of feeding this hot spot. And currently, that hot spot is what feeds the volcanoes in Hawaii. Now, only the islands closest to that hot spot are volcanically active. As you get further away from the current location of the hot spot in Hawaii, which is made up of 5 or 6 islands, they're not volcanic anymore. There's no eruptions going on the further you get away. And that's because underneath where the hot spot is now, where that mantle plume is now, is where the current location of the largest Hawaiian island is. But if you look at the seafloor, after mapping the seafloor, if you look at it, you can actually see a chain extending away from the Hawaiian Islands and then a bend of it all the way up. What this indicates is that while that mantle plume, that hot spot, stayed there, the Pacific Plate over time has moved over it. Not only has it moved over it, it actually changed direction. Initially, the Pacific Plate, because this is the newest volcano, this is the newest volcanic feature, so therefore the oldest one is way over here. So initially, this part of the Pacific Plate was over here, and it was moving straight north. Then all of a sudden, it started to shift and kind of move a different direction, all due to plate tectonics. And we can track that movement in these now underwater seamounts. These were all volcanic at one point, but the weathering and erosion and ocean and water has broken those things down, and now those volcanic mountains aren't above sea level anymore. They're all kind of ground down. And that's why with the Hawaiian Islands, let's see, yeah, here we go. With the Hawaiian Islands, you can actually see that occurring. The current Hawaiian island that's most volcanically active is is that Hawaii? Is that the name of the island? Maui, I believe, is also volcanic, but as you get further away, not only are they getting smaller, but they're no longer volcanic. This was volcanic 3.8 to 5.6 million years ago, and you can see Hawaii is now been over that hot spot for 0.7 million years, so 700,000 years, all the way to the present. But yeah, so anyway, you can see the Hawaiian seamounts and the Emperor seamounts. These were all volcanoes at one point, but as we see, they're starting to get ground down due to weather and erosion, and that eventually will happen to the big island of Hawaii as it continues to move, and then a new volcano and a new island will be created. Kind of cool, I think. So anyway, so further evidence of plate tectonics. You know what? Let me give you another part of the super secret code. It is the number 3. One more time, 3. One more time at you, the number 3. So that's the next part of the super secret code. So think so far I've given you 4 parts. So we're going to pause here. When we come back, we'll talk about current methods, ways we're currently detecting plate motion. We've made it a lot easier on ourselves recently with technology. So anyway, more on that when we come back.